let's compare these two versions, shall we? So here's a traditional one. F of theta is all this stuff, and we can declare these the coefficients are given as integrals. By the way, we're just going to set b sub 0. This doesn't define a b sub 0, but let's define a b sub 0 for us. I'll write it down here. B sub 0 is just 0. It's just always equal to 0. That's why it never shows up. All right. So here's what we've got. And here is what we're going to use to convert between the two. So e to the I theta is cosine theta plus I sine theta. E to the minus I theta is cosine theta minus I sine theta. And you may recall, so solving for the trig functions in terms of the exponentials, you get this. This was done on Friday. This is on earlier on in this set of slides. So here's the modern version. Here the coefficients are an and bn. Here we have one family of coefficients, cn, and cn's are given like this. So how do I get from one to the other? The idea is, let's say to get from the modern to the traditional, wherever you see an e to the I something, you replace it with that. You replace it with the right-hand side, which gives it back to you in terms of sines and cosines. And then you kind of go from there. So let's see that. So this is actually, we're going to go from the traditional to the modern at this point. So here's the traditional form. I'm going to use these formulas, substitute in for cosine theta and sine theta, substitute those in here, the complex exponentials, using these expressions, and then do some rearranging and simplifying. So plug them right in like this. Okay. And rearrange things a little bit, and okay, all right. You don't really have to know this in detail, but just you're taking this, and now I'm collecting terms with the same exponent. So I'm going to collect these two terms. This L here, that's a Microsoft PowerPoint glitch. That should be an ellipsis, like 3 dots. Okay, so it continues to the right, continues to the left, and this is also 3 dots. So the point is, this is f of theta, traditional form. We want to express it in modern form like this. If, as we group these terms according to their exponents, then here is the conversion. If I have the traditional coefficients an and bn, this tells you what the cn's are in terms of the an and bn. So if you know the an and the bn, this conversion tells you what the cn's are. So this is for n being 0 or positive. This is for c sub n, and this is for c sub minus n. The only difference is here. These are complex conjugates of each other. This is an minus I bn, and this is an plus I bn, all divided by 2. So that's how to get from the traditional to the modern. And then to get, if you have the modern form and you want to get back the traditional form, you just invert these two equations and you solve for an and bn in terms of cn. And so that's done right here for us. So notice that an is what you get if you just add cn and cn and c minus n. Just add these two equations together, out pops an. And then bn is cn minus c of minus n all times I. So this is all you have to take with you to convert between the traditional form and the modern form. So it's often easier to actually compute with the Fourier series in the modern form. And then if you want to know the traditional sines and cosines, you use these to convert. We won't actually do an example of this. It's just there if you want it. All right, so in the modern form, if we want to go into the time domain from the angle domain into the time domain, we make the same substitution. So theta is omega t. And so y sub t is now the waveform as a function of t. This will be f of omega t. So f is the omega t is the angle, and f is the same function as it was before. Just plug that in all over, and you can express it in many different ways. In omega t, in 2 pi ft, or in 2 pi over capital T. And then I've got similar ways of expressing the coefficients, which will be exactly the same as they were for f. And we won't do an example of this. I will do something. I will actually do the square wave. So we know the traditional form for the square wave, right? It's that triangle wave. So the square wave amplitude 1, just make it simple, is f of, so y of t is f of omega t, which is f of 2 pi f of t. And that's, 4 over pi times sine of 2 pi ft plus 1/3 sine of 3 times that, which is 6 pi ft plus 1/5 sine of, what's the next one? 10. Okay. So let's write down the A coefficients and B coefficients. So it's an odd function, so we know all the A's are 0. Great. Okay. A 0, A1. These are all 0. Well, B0 is always 0. What about B1? It's 4 over pi. So regardless of what's inside there, regardless of how I'm representing the actual angle, the B coefficient is 4 over pi for amplitude 1. What's B2? It's 0 because there is no second harmonic. I only have the odd harmonics. So B2 is 0. So there's no 4 pi ft contribution, so that has to be 0. B3 is 4 over 3 pi. So I get the 1/3. And then B4 is 0. And then B5 is 4 over 5 pi. And so forth. So now what I'm going to do, go back to this conversion here and find what the C's are. So what are the C's? So the 0 C is A. I have B0 is 0, so this is just 0. So C0 is 0. what's C1?
It's negative 4 pi I.
So it's
negative. So negative 2 pi I.
So it's negative 4 over pi times I divided by 2. So this is a negative 2 pi I. Is that right? There's a...
Yeah, if it's simple math, I can do it until I write it down.
Oh, it's over pi, right? Okay.
You don't always move something around.
So negative 2 over pi times I. Okay. And C2? 0. C3? That's going to be a third of this. Over 3 pi. And then C4?
0.
C5?
Negative 2 over 5
Negative 2 over 5 pi times I. Okay, and so on. Now, what's C negative? Yeah, so it's the same, except it's plus. So this is 2 over pi times I. C negative 2?
0.
0. C negative 3?
Just change the sign on C3.
2 over 3 pi times I, and so on. Okay, going that way. So if I plot the frequency, give the frequency domain plot, this is going to be, there's the fundamental F, 2F, 3F, 4F. But now I'm going in the negative frequencies as well. So I'm going to have plots on the other side. This is minus F, minus 2F, minus 3F. And now what I'm going to plot, because these are complex numbers, I'll just plot their absolute values, or their norms, if you like. So that just means I take the I off. So what do I get? I get, in the plus direction, I get a minus 2 over pi, which is, say, down here. So it's minus 2 over pi. Oh, I'm sorry. Norm. It's plus 2 over. I'm taking the norm, so it's actually plus 2 over pi. So it's like that. And then at 3f, it's going to be a third of that. And then 4f it's 0. And then 5f, it's going to be a fifth of that. So something like that. And then on the other side, I get the same thing. I get that. I get that. And so on. So now the frequency spectrum actually goes in both directions. Okay. And if I want to, the bandwidth, if I want to take some approximation to the function, and a natural way of doing it would be to take some positive cutoff and the equivalent negative cutoff. And just have all, so I'll have, maybe if I cut that off, I'll have these terms and those terms, and then that would be it. Okay. And that's equivalent to the traditional cutoff, the two-term cutoff in the traditional form. But so the only point is your frequencies can be negative as well. All right. Questions on that? All right. So we're ready to go. Talk about Fourier transforms. So I'll start off Fourier transforms. I'll introduce them. We'll take another break, and then we'll come back and we'll do some more stuff. I'm actually close to being out of slides, so some of the next hour will be on the board. So let's compare Fourier series with Fourier transforms. The Fourier series, it's a discrete series. It's an infinite sum, discrete sum of terms that represent a periodic function. The frequencies are integer multiples of a fundamental frequency. So the spectrum associated with the Fourier series consists of discrete frequency components. So the frequency function is non-zero only at discrete points which are integer multiples of the fundamental. Here's what a Fourier transform does. Now we want to represent an aperiodic function, such as a pulse. So the spectrum, in this case, we want to decompose a pulse into frequencies. But a pulse is not periodic. So now the frequencies will not be, it doesn't have a fundamental frequency anymore. So I'm not going to get integer multiples. I'm not going to get integer harmonics of the fundamental frequency anymore. What instead I will get is the spectrum is going to be a continuum of frequencies. I am going to, in some sense, maybe all possible frequencies, all values, all real numbers, from minus infinity to plus infinity, are somehow contributing to the pulse. So not discrete multiples of the fundamental anymore, but in fact all possible frequencies might be contributing to the pulse. So the Fourier transform allows you to find the spectrum giving the relative contribution of all the frequencies, but now it's not really a function giving the frequency itself. It's sort of giving you a function. It gives you the frequency density. So how, in some small interval, what contribution are you getting from these frequencies to form the pulse? So the Fourier transform is a continuous version of the Fourier series. Fourier series, you got a discrete sum of things. Well, we're now going to make this a continuous sum of frequencies. And a continuous sum is an integral. So usually when we go from discrete to continuous sums, or when we go from discrete case to continuous case, we've seen that before. Sums often just turn into integrals. So we saw this with random variables. Well, the same thing's true here. The Fourier spectrum is, with the pulse is going to be made up of a continuous sum of constituent frequencies. And what those frequencies are, and the strength of their contributions, that's what we get by analyzing the pulse. All right. So we are breaking up a pulse into its constituent frequencies, but now these frequencies are on a continuum. The frequencies that make up the pulse are on a continuum. So here is some aperiodic function of time, y sub t. So this is a sort of a waveform. Think of a pulse. Think of some kind of pulse with some funny shape to it. But as t goes to minus infinity and as t goes to plus infinity, the pulse should diminish to zero. So it really has to, it can't be, it's got to go away as you limit. So before we had a sum here. We had a sum of a coefficient giving the frequency contribution times a complex exponential in the modern form. Okay? But here, now we have an integral. So what we are integrating is, we're integrating all of these possible complex exponentials for all possible frequencies f. So we're integrating df times some strength of a contribution, and we're integrating all this from minus infinity to plus infinity. So all possible frequencies might be contributing at this point. This is called the inverse Fourier transform, this formula right here. So this is if you know what each frequency strength is, that's S of f. That's the frequency domain plot. Using this integral, that allows you to recover the actual waveform, the actual function. And we need to go in the other direction. So given a waveform, y sub t, how do you get the frequency domain plot out of it? Well, you'd use this integral, which is similar to the integrals we had in the discrete case. So let's go back to the discrete case just a second. So here, for example, the coefficients, these are now discrete because the signal is periodic. These are discrete coefficients. They're given by integrals over one period of the function. Here, this is similar. This is a similar integral, but you have to look at the entire function from minus infinity to plus infinity dt because it's not periodic anymore. So you have to look at the global function. But again, you multiply it by these complex exponentials, and when you integrate, that gives you the strength of this particular frequency contribution, which you can then plug back up here and recover the function. So what's changed between the Fourier transform and the previous Fourier series is, well, two things have really changed. One, the discrete sum has now become an integral, and instead of having discrete coefficients here, now I have a number associated with every real frequency, okay, which I then integrate times the corresponding waveform. I integrate this to recover the waveform. The other difference is here, to actually find that frequency contribution for one particular frequency f, I got to integrate the function over, not over a single period anymore, but over the entire real line, minus infinity and plus infinity. But notice how similar these two things are. The transform and the inverse transform, they only differ by a minus sign right there. So actually, computationally speaking, these are essentially equivalent. Once you compute the transform, you can easily just tweak it to get the inverse transform and vice versa. So these two computations are usually completely redundant. You really only have to do one of these integrals, and just by some basic principles, you can get the other one very easily. All right. So let's do an example. Square pulse. So I'll talk through this. We'll take a break, and then we'll actually do this integral. So we've got the tools to actually compute this integral. So we're going to do it. So here's a square pulse with amplitude A and a lifetime of tau. So tau is now the duration of the pulse. So here's the signal as a function of time. It's 0. There's no signal at all up until minus tau over 2, where the signal jumps up to some constant A, the amplitude. And then it jumps back to 0 at plus tau over 2 and stays 0 beyond that. So tau is a parameter. It tells you the duration of the pulse, how long the pulse is lasting. And A, it tells you the amplitude. All right. So how do we represent this function? Well, y of t is equal to A, provided t is between minus tau over 2 and plus tau over 2. And I'll add to that. I'll say that y of t is equal to 0 otherwise. All right. So, what are the frequencies of the sine curves given by of the basic waves that can add up together to get this pulse? So the contribution of each frequency is given like this. It's given as an integral from it's from minus infinity to plus infinity, but since y of t is 0, except in this range, the minus infinity to plus infinity, you only have to integrate from minus tau over 2 to plus tau over 2. And this is y of t here. So that's y of t, which is just a constant a, times this complex exponential, minus I 2 pi ft dt. And we'll show after the break that this is actually equal to the amplitude times this function, which is basically the sine of the frequency divided by the frequency in there. There's a factor of pi tau here and a factor of pi in the numerator. This function has a name. It's called the sinc function, written S-I-N-C. What is it? I better not say that. It's so sinc of x. I'll just write sinc of x is equal to sine of x divided by x, I think. So this is some constant times the sinc function. I think I might be missing a pi in here somewhere. Someone wants to look it up. That's fine.
I think it should be pi x.
Pi x in the denominator?
In both.
In both?
Sine of pi x divided by x.
Okay. So this curve looks like the sinc function. So I graphed the sinc function and it looked like this. Well, you'll see it in a second. It's a sine curve, but it's dampened in both directions. So I divide by x. So I take sine of x and divide by x. And strictly speaking, it's undefined at x equals 0, because then x is the numerator. But you get 0 over 0. If you take the limit in either direction, you get 1. So we might as well just extend it to make it continuous and defined everywhere. But because of the 1 over x in the x in the denominator, the amplitude is going to dampen out. It's going to decrease as 1 over x as you get further. So most of the bulk of the frequency contribution is right here. It's right in the middle. And you get some frequency contributions on either side, but they diminish fairly quickly. So if you integrate regular sine curves multiplied by these frequencies, you integrate that from minus infinity to plus infinity, you will actually recover the square wave, the square pulse, exactly this way. All right. Let's take a break, and we'll come back. We'll do this integral, and we'll talk a little bit more non-technical stuff. Some more of that.
Okay, sounds good. Thank you. Yes, sir. Sounds great. Thank you very much.
Realize what all has to do. In your face!
I missed the part of that. It just sounded wrong. It said something about pumping in your face. And
Carbs.
Oh, alright. Thank you for picking that. In my head, it was going off in different nasty things.
It's one of those. The daydreams turn into the day nightmares.
Less.
Well, you have less.
Yeah, less compatible. So because of that,
I just wonder if what is the real like, I can't find a good example. Googling the shit out of it. That's not going to the special analysis, but I mean, you don't see any examples, it's just hard formulas.
Yeah. That's really just what happens. I don't know. Time is something else. You never remember getting paid every day.
That's a lot of weird. It's like how your son's always hitting on June.
That's true.
Yeah.
I don't know what the hell's going on.
I about had to whip a 4-year-old Saturday.
That's why you.
It was first time too.
Yeah, it was like we were there for less than 5 minutes. You want to see my room? Back off, son.
I expect nothing less from Ricky Bobby. Beating up the boys.
You don't have to worry about when he shows the room unless he closes the door behind him.
Close the door. What?
Look at my Spider-Man sheets.
They're real comfy, John.
I have the matching undies.
Sad thing is like
But I'd probably actually be just as far as I would go with that one.
it would be.
There's a lot of other stuff you can do with the encoding and check.
Doesn't cost
Maybe
that
you look
slab.
at set value. Not really things you can do
I'm not going to laugh
using
at
for
you.
data value rather than just make it simple. Which is why they're not really. In theory, that's if I'm smart, if I'm smart programming, or I'm smart piece of hardware. That's good enough not a big chunk of one which is therefore enough to get data through. Less lower bandwidth than here.
You just gotta use all this. I think the problem was like the first time we went.
Or you should say I'm getting exactly that.
No, it's not. Yeah, that might have been.
That would be one of the.
That can actually make a big difference in some
things
of
that go
the
into the power results.
Yeah,
Give it your bandwidth in your environment and your system.
Yeah, whereas like
And my environment, my system are what the data is. It's not simply data.
what's the rest of
All right. Get going then? Got everybody? Looks like we got everybody. Okay.
Yeah, better.
I need to. Here's the sync function again. So here it's just it's from the origin on. So that's what it actually looks like. And so the frequency domain function for the square pulse is this. And in this graph, we're using x, but in the graph, x is the same as tau. So that's the scale we're using. And this goes from 1x or tau, then down to 0, and this occurs when f is equal to what? So where do I get 0? Well, it's 1 over x, it says right here. But in terms of what angle do I get 0?
90 degrees.
90 degrees. So this is 90 degrees, or it's pi over 2. Okay. So in order for this to be pi over 2, no, I'm sorry, not 90.
Guys, okay, bragging.
You had me going there.
Whoa. Your confusion is so profound that it affected the teacher.
Don't hit.
Where do you, I'll ask again.
0 degrees.
Someone other than Allison.
Whatever 0 degrees. Or pi.
Okay. Pi. Well, okay, he answered. I'll let him answer. You other.
I remember my chart wrong, so sorry.
It's a chart's fault.
If it was
So-
cosine, it would have been 90 degrees.
You get an angle of pi. So that tells you what f has to be in terms of pi and tau. Okay. Well, that's a reasonable. So the bulk of the contribution comes from frequencies between these values, 0 and in this case it would be 1 over tau. Okay. Now you get some contributions from 1 over tau to 2 over tau, but less and diminishing it further as you go. Okay. Yes, question.
Is that would that just be like noise on the line, or because I mean if I'm thinking of like the block or the what's it called the square deal, I'm just thinking of there's something or there's nothing, not that there's something you can measure or little squiggles to probably oversimplify it way too much.
Yeah, these are two different domains, so let's be careful. This is in the time domain.
Okay.
So this is a function of time. This is the frequency domain.
Okay.
So this is a function of frequency. So no noise creeping in here.
Okay.
In terms of absolute frequency contribution, these are the frequencies you get. If you put these frequencies together by the integral, you integrate from -3 to plus infinity, you will in fact get the square pulse back again exactly.
Okay.
Back in the time domain. So let's just talk a little bit. I'm going to save the integral for last. I want to talk a little bit more about bandwidth here. The bandwidth is, again, it's infinite. All right. So you're going to get frequency contributions on both sides of the origin going out to infinity in both directions. But in terms of, let's say you wanted to transmit a square pulse through a channel, and you are only allowed a certain finite bandwidth, and for the moment we'll consider that bandwidth just to be centered at frequency 0, just for simplicity at the moment. So suppose you are only allowed frequencies, or maybe your equipment can only handle frequencies between -1 over tau and +1 over tau. Or maybe the medium absorbs frequencies that are higher than that. Or maybe FCC won't let you broadcast at frequencies beyond outside of that range. So you're only allowed from -1 over tau to +1 over tau. Then effectively, what you're going to send is some signal whose frequency plot looks like this, except when you get here, it's just going to be cut off. So maybe you cut that off artificially to satisfy the FCC, or maybe those frequencies are just absorbed by the medium, or whatever. They're not transmitted correctly by your equipment. But anyway, you can imagine that if you're limited to... I can't walk over there. I've got to use this. On camera. If you're limited to frequencies in this interval, then all this outside stuff is basically you can't transmit it. It's going to be gone. So you're going to have an altered frequency plot. So your frequency plot is not going to be S of f. It's going to be some S prime of f, which is, hopefully, it'll be close enough to S of f, but it won't be exactly S of f because it's got to be 0 outside of the allowed interval. So what happens if you take S prime of f and you go back using the inverse transform to recover the wave function? What are you going to get? You're going to get an altered, your wave is going to look different. Basically, it will kind of look like the square pulse, but it's going to be distorted. It's not going to look exactly the same. Maybe it's got some fuzziness here, and you've got some bumps, and it kind of trails off, and you don't get a sharp line like that. Okay. This is typically what happens. If you limit your bandwidth to a certain amount, and you have to cut off frequencies that are outside that bandwidth for whatever reason, then what you're going to transmit is not exactly what you want. It's going to be some distorted version of what you want. And this is what leads to, well, it leads to static, it leads to noise if you're listening to an analog radio signal. It also leads to bit errors because you're not transmitting. So let's say you want to transmit a single bit. And a single bit is, a 1 bit is represented by amplitude A, and maybe a 0 bit is represented by amplitude A over 2, say. You're just transmitting a single bit. Well, if you're cut off too much, this might be distorted in such a way, it's distorted so much that the person who's sampling on the other end, trying to recover your bit, recovers the wrong bit. So this will lead to bit errors. So the guy on the other end is sampling your signal, and he samples, 3A over 4, 3/4 A. And maybe he takes the closest, and maybe he gets the wrong value that way. Okay. So that's what happens if the bandwidth is cut off. Now, if you're allowed more bandwidth, then the frequency plot will be closer and closer to the true one, which is SFX. And so you will transmit a square pulse with better and better fidelity, and so you have less chance of a bit error. But now suppose you have you just have one bandwidth, and that's all you're allowed, or that's all you can transmit for whatever reason. How do you get a square pulse? How do you get a square pulse as accurately as you can? Well, you can increase tau. If you increase tau, then what happens to this plot is you're basically squeezing it. So as you increase tau, you're squeezing this plot so you can fit more of the actual frequency plot into the allowed bandwidth, right? Into the allowed interval. So that will get you closer to a true square pulse that you send. But what are you doing when you squeeze this? You're increasing tau, which does what? What's tau? Is the duration. So you're actually increasing the duration of the pulse. So what that means is you're going to transmit less. It takes longer to transmit a single bit. You'll have less error, but now it's taking longer. There's no real way to get around this trade-off. If you want to transmit bits at a high rate, you have to make these pulses really short, have short duration. But when you make tau small, the frequency plot does the opposite. It stretches out. Okay, so the frequency plot goes with 1 over tau. Okay, and so if you have a fixed bandwidth, if you have a fixed interval that you're allowed to transmit in, and your frequency plot is really broad, you only get a small fraction of it in the allowed place, and so you're going to get a highly distorted signal. So you can't decrease the duration too much without lots of distortion, given that the bandwidth is going to be the same. Does that make sense? So that's the real trade-off between bandwidth and data rate. Pulses you can get a good pulse with high fidelity if the duration is long, but if you make it too short, given that you have a finite bandwidth, it's distorted. All right, questions on anything? All right, so let's go back. Let's do this interval down here. All right, that's on the next slide, and this is the last slide. Oh, here it is. Where is it? There we go. Okay. So here it is. I'm going from minus power to the plus power. So this is all just from the previous slide, this equation right here. First thing I do, I can pull out A. It's just a constant, so I pull that outside, and I get that. Okay. What's the variable of integration here? It's T. Okay. F, so you should think of F as some fixed quantity, and what we're getting out, this entire integral will be a value that depends on F. All right, how do you want to do this? There are two ways. You can take this, plug in Euler's formula for it, or you could do a linear change of variables at this point. So do you have a preference? I can't change the slide, so it's whatever the slide gives. But you can do it either way. Time permitting, maybe we'll do it both ways. All right. So, always good to have a little sidebar when you're doing integrals to record stuff that you're doing. So, to do a change of variables, we'll let u be this whole exponent. So I want to get the integral to be e to the u du. That's what we want. So I got to set u equal to that whole exponent, which is minus I times 2 pi times f times t. So that's all up there. And now I got to change the dt into a du. So to do that, I take the derivative of u with respect to t and multiply both sides by dt, and the derivative is just minus I 2 pi f. So the t disappears. So I get that. And so solving for dt is du over all of that, minus I 2 pi f. Okay, so standard linear change of variables. The fact that I have an imaginary constant in here, don't worry about it, it's fine. So when I change these variables, as t goes from minus pi over 2, minus tau over 2 to plus tau over 2, what does u do? Well, if I plug minus tau over 2 in for t up here, and simplify, I get an I pi f tau. So I'm plugging minus pi over tau, minus tau over 2 up here in for t, and seeing what u equals. And it equals I pi f tau. And likewise, if I plug in plus tau over 2 up here, I can get a minus I tau pi. That thing. So those are going to change the limits of integration. So the next equation now looks like this. Instead of going from minus tau over 2 to plus tau over 2, I go from I pi f tau to minus I pi f tau. So in pictures, in the complex plane, I'm going from I pi f tau to minus I pi f tau. Those are both pure imaginaries, so I'm going down this way. That's the path. That's the path we're taking in the complex plane. Okay? And then I get a e to the u out of here just by substituting. And then again, substituting dt, plugging that in, I get that thing, and then I can pull that constant out. So now all that goes outside, and I'm left with this constant outside. And inside, I just have this integral. Okay. For simplicity, I'll just call this big thing, I'll just call it c, just so I don't have to carry it around with me everywhere. So this is c times the same integral. All right, now what? What's the next step? Don't peek. Antiderivative of e to the u is e to the u. Good. So I can get rid of the integral now. Sorry, so that's what c is. I get rid of the integral, and what I do is I evaluate e to the u at u equals that thing minus e to the u evaluated at u equals that thing. So that gives me all that times c. So it's e to the minus pi f tau minus e to the plus I pi f tau. Subtract those two. Okay. What's next? Now I got to use Euler's theorem. This is, and the reason is because if I use Euler's formula here, I'll get to simplify a lot of stuff. So you'll see a lot of stuff will cancel. So now I can plug in Euler's formula in two places, right here and right here. So I get C still outside. And here I'll get cosine of minus pi f tau plus I sine of minus pi f tau. Just plugging in that formula. So theta is now minus pi f tau. Minus this thing, which is theta is now plus pi f tau. So it's minus cosine minus pi. All right. Yeah. Just plugging that in twice. Okay, and now I know things about cosine of minus an angle is the same as cosine of the angle. And sine of minus an angle is negative sine of the angle. So that changes, and I'm left with that. And now the cosines cancel out. And the sine terms are now equal. So I can just add them. And it's the same as multiplying by 2. So I get that. Questions? Looks good. Now I just multiply this back by C, which is this, and just simplify. So notice I got a minus 2i there, I got a minus 2i there, so those just go away. And so I'm finally left with that. And that's just what I had on 2 slides ago. It's the same thing. Questions on how that works? All right. So you're all happy with this?
Sir, I'm still copying it
You're still copying it down?
These slides aren't updated on ours.
now. It's handwritten.
But these are not on your... Oh, no. That's bad. That confirms my suspicion from before. These are not the latest slides.
I blame Wade.
Yeah.
I will make sure that you get these slides somehow by going in and talking to somebody. Okay.
It's on there. It's just handwritten.
Oh, it's handwritten.
It is.
Oh, so yeah, so you have the handwritten version. Okay. So interesting. So these slides are different from the ones you have. That should be true.
Yeah, it's just this.
It's just
this
last
section.
sample.
Okay. Just well, that's really
We've
the
got
big
this
difference.
spread over 5 slides of handwritten
Oh, okay.
stuff.
All right. Yeah, because I hand wrote these last time, and then I typeset it. But I guess you didn't get the typeset version. All right. So I'll make sure that you've got it.
I blame Wade.
All right. Any questions about the interval? I think this is my last slide. Do you want to see it the other way? Sure. Okay.
Easier.
Do it the other way. I'll leave that here.
I'm seeing some short shots.
Let's see. If this is my last slide. All right. Yeah. So that is the last slide. Okay. Yeah. Still copying, great. Let me know when you're done. Well, don't let me know. I'll just ask.
Yes, sir.
All right. So when you're done copying, I'll put up the screen, and then I get the whole board to work with. So this is going to be from minus tau over 2. So this is S of f. Plus tau over 2. A times e to the minus I times 2 pi f t d. Okay, that's what we started with, right? Yes. Okay. So the alternate method is to, right from the beginning, put in Euler's formula, use Euler's formula to convert that to sines and cosines. Well, take the a out. It's easy to do. So I'll do that simultaneously. And now I get a cosine of 2 pi f t. It's minus I, so it's going to be a minus I sine 2 pi f t.
all that. So now, distribute it. I'm going to have to use the change of variables eventually anyway. And now let's. I won't use u. I'll use a different variable. Let's use y. So what we want y to be is to be that thing. So then we can take cosine of y and sine of y. So y is going to equal 2 pi ft. That's the best change of variables, right? Because the whole point of changing variables is to get it so you know what the antiderivative is. You want to get something simple function. All right, but then we got to replace a dt with a dy. So dy over dt, that's the derivative, is just going to be 2 pi f. Solving for dt, we get dt is equal to dy divided by 2 pi f. Okay? And we're going to do that in both places, but now we got to worry about the limits of integration. So is t is equal to minus tau over 2. Pi's and tau's get confusing. Minus tau over 2. What's y? So the 2 cancels, and I'm left with negative pi f tau. And if t is plus tau over 2, then y is positive pi f tau. Pi f tau. So I'm going to do that in both places. So I get an a integral of, and this is going from minus pi f tau to plus pi f tau of cosine y dy over 2 pi f minus I tau over 2, plus tau over 2. Sine of y dy over 2 pi. Did I do that right?
Shouldn't the towels or 2?
Oh, yeah. Same thing, minus pi f tau to plus pi f tau. This marker smells really good. That's why I'm making mistakes. But I don't care. All right. Now what? Now I can get rid of the integrals by doing the antiderivative thing. Are we done with this slide? Come home. All right. Anyone else not done with this slide? Great. Okay. I'm gonna turn this off.